Here are the first few prime numbers on a line, and something jumps out right at the start. 3, 5, 7. 3 primes in a row, and each one sits exactly 2 steps past the one before. A tidy little cluster of 3, packed as tightly as primes can possibly be. Now, tight pairs of primes 2 apart are not rare at all. 11 and 13, 17 and 19, 29 and 31. These twin pairs keep showing up no matter how far out you count, thousands of them, and as far as anyone has ever looked, they never stop coming. So a pair 2 apart is an old familiar sight, but a run of 3, each 2 apart, like 3, 5, 7, that is a different animal. And here is the strange part. You can scan the entire number line as far as any computer has ever pushed, and you will never find another one. Not one. 3, 5, and 7 is the only time it ever happens, anywhere, forever. By the end of this, you will know exactly why, and be able to prove it yourself in a single line. Before the reason, it is worth feeling how completely the search fails, because your instinct says a pattern this simple should turn up again somewhere. So go looking. Start just past 7, 5, 7, 9. That would do it, except 9 is 3 times 3, not prime. Try 11, 13, 15. The first 2 are prime, but 15 is 3 times 5. Push on. 17, 19, 21, and 21 is 3 times 7. Jump way ahead to 101, 103, 105. The first 2 are both prime, and then 105 falls apart into 3 times 35. Notice what keeps happening. Every single time, one of the 3 numbers is a multiple of 3, and so the whole run collapses. It is never the same position, and it is never bad luck. A computer search runs this all the way out past 2 million and finds exactly 1 triple of this shape in the entire range, the one we started with, 3, 5, 7. Something is actively blocking every other candidate. That something is not chance. It is a rule, and once you see it, you cannot unsee it. Here is the whole reason, and it fits in a single idea. Forget primes for a second, and just take any 3 numbers, spaced 2 apart. Some number, then 2 more, then 2 more. Look only at their remainders when you divide by 3. The first number leaves some remainder, either 0, 1, or 2. Add 2, and the remainder shifts. Add 2 again, and it shifts once more. By the time you have all 3 numbers, their 3 remainders have marched through every possibility, 0 and 1 and 2 in some order, with no repeats. That is forced. 3 numbers, 2 apart, always land on all 3 remainders at once, and a remainder of 0 means divisible by 3. So one of your 3 numbers is always a multiple of 3, guaranteed every time, no exceptions. Now bring the primes back. If all 3 are supposed to be prime, then the one that is a multiple of 3 has to be 3 itself, because 3 is the only prime that 3 divides. That pins the whole trio down. The smallest is 3, and the run can only be 3, 5, 7. Every other starting point puts a genuine multiple of 3, something bigger than 3, right in the middle of your trio and kills it. That is the entire proof. The title says these primes defy logic, but it is the exact opposite. Logic is what forbids any second copy. So the natural worry is that this dooms every tight little prime pattern. It does not, and seeing why is the fun part. Go back to the twins, plain pairs 2 apart. 11 and 13. Take their remainders when you divide by 3. A pair is only 2 numbers, so it can only cover 2 of the 3 remainders, never all of them. There is always a remainder left over, that neither one lands on. So a pair can dodge the multiple of 3 trap completely, and it usually does. Nothing forces a twin pair to contain a multiple of 3, which is exactly why they are free to keep appearing, and keep appearing they do. Below 100 there are 8 twin pairs, below 1,000, 35, below 1,000,000, over 8,000 of them, and the count just keeps climbing the further you go. Whether it climbs forever is one of the oldest open questions in all of mathematics. The twin prime conjecture, and essentially everyone believes the answer is yes, even though no one has managed to prove it. The point for us is the contrast. A trio 2 apart is forbidden after the very first one. A pair 2 apart runs on, and the only difference between them is whether the pattern is forced to swallow a multiple of 3. That single difference turns into a clean rule for which prime clusters are even possible, and it is worth stating carefully. A pattern of gaps is allowed to repeat only if it passes a test at every prime. Take the pattern, look at its remainders when you divide by 3, and it must leave at least one remainder unused. Then check the same thing for division by 5, and by 7, and so on for every prime. As long as the pattern always misses at least one remainder, nothing is forced to be composite, and the cluster is free to occur again and again. Fail the test at even one prime, and the pattern is dead after at most a single appearance. 3 primes 2 apart is the pattern 0, 2, 4, and we just saw it uses up all 3 remainders mod 3. It fails the test at the very first prime. But watch what happens if you nudge the third number out. Take 0, 2, 6 instead, a pair 2 apart, and then a third one 4 beyond. Its remainders mod 3 are 0 and 2. It skips the remainder 1 entirely, so it passes, and it should be able to repeat, and it does. 5, 7, 11, 11, 13, 17, 17, 19, 23. These triples keep coming, because they were never forbidden in the first place. Once you have the test, you can hunt for the tightest legal clusters on purpose, and they are lovely. There is a mirror image of that last triple. The pattern 0, 4, 6, a prime, then 1 4 steps up, then 1 6 up. 7, 11, 13, 13, 17, 19, 37, 41, 43. It passes the same test at 3, so it too shows up forever. And you can go one better. Stack the 2 allowed triples together and you get 4 primes in the tight block 0, 2, 6, 8, which is the closest 4 primes are ever allowed to sit once you are past the very small numbers. 5, 7, 11, 13 is the first, then 11, 13, 17, 19. Then a big gap and 101, 103, 107, 109, 4 primes packed into a span of 8. These quadruplets are rare, but they refuse to quit. There are 259 of those first triples alone, below 100,000. Every one of these patterns threads the needle at 3, and at 5, and at every prime after, so nothing ever forces a composite into the group. They are the tightest clusters the rules permit, and the rules permit them endlessly. All of this points at one sweeping statement that mathematicians believe ties the whole subject together. It says that the divisibility test is not just necessary, it is the only thing that ever matters. Any pattern of gaps that survives the test at every prime, that always leaves some remainder unused, will occur infinitely often. In other words, the single reason 3, 5, 7 never repeats is the multiple of 3 obstruction. And once a pattern has no obstruction like that anywhere, nothing can stop it from happening again and again forever. This is called the prime k-tuple conjecture, written down by Hardy and Littlewood back in 1923. Now, the honest word there is conjecture. This has not been proven. It is one of the deepest open problems in number theory, and proving it would settle the twin prime question and 100 others in a single stroke. But the evidence for it is enormous. The counts line up beautifully with what it predicts, and almost no one doubts it is true. So we are left with a sharp and slightly funny situation. The one pattern we can say something certain about is 3, 5, 7, and what we can say is that it is banned forever. The patterns we cannot quite pin down are all the ones that seem to go on without end. Even without the full conjecture, the last decade cracked open a piece of it that had been stuck for over a century, and it is worth telling. Nobody can yet prove there are infinitely many primes exactly 2 apart. But in 2013, a mathematician named Yitang Zhang proved something almost as good, and it stunned the field. He showed that there are infinitely many pairs of primes that sit within 70 million of each other. 70 million sounds enormous next to 2, but the miracle was getting any fixed number at all, the first finite bound in history on how close primes are forced to keep coming. And once the door was open, it moved fast. Within months, James Maynard found a sharper method and pulled the bound down from 70 million to 600. A large online collaboration then ground it further, all the way down to 246. So today it is a proven fact that infinitely many primes come within 246 of each other, even if we still cannot reach the twins at a gap of 2. That narrow space between 246 and 2 is where one of the great unsolved problems now lives. And through all of it, sitting quietly off to the side, 3, 5, 7 stays exactly as certain as it ever was. So that is the whole shape of it. 3, 5, 7 is a run of 3 primes each 2 apart, and it is the only one there will ever be. Line up any 3 numbers spaced 2 apart, look at their remainders on division by 3, and one of them is always a multiple of 3. For all 3 to be prime, that multiple has to be 3 itself, which locks the trio down to 3, 5, 7 and nothing else. Every tighter question turns on that same test. A pair 2 apart skips a remainder and is free to repeat, which is why the twin primes keep coming. The triples spaced 0, 2, 6 and the quadruplets packed into a span of 8 all thread the needle at every prime and are believed to run on forever. Only the patterns that are forced to contain a multiple of some prime are shut down, and 3, 5, 7 is the smallest and most perfect example of that. If there is one thing to carry away, it is that a pattern in the primes is impossible for exactly one reason: being forced to swallow a divisor, and possible the moment it escapes that trap. 3, 5, 7 is the one cluster the rules forbid outright, and we can be as sure it never returns as we are sure of anything in mathematics, while the twin primes right beside it stay open to this day. This was one more in a series on the questions the primes refuse to settle quietly. Stay for the rest.